Pure aluminum is easy to shape, but in high-stress applications, that formability is a liability. Under blunt force, its metallic lattice simply yields. To increase its resistance, material scientists rely on chemical alloying. For aluminum, the standard upgrade is introducing copper directly into the metallic matrix. This process is a continuous exercise in multivariable trade-offs. Every structural gain carries a hidden cost. We are going to track exactly what happens when we push an aluminum-copper alloy to its maximum chemical solubility and subject it to extreme mechanical stress. Engineering a material for high physical strength introduces microscopic structural vulnerabilities that only aggressive environments expose. This investigation centers on three interacting variables: chemical alloying limits, severe plastic deformation, and an aggressive halide environment. Specifically, we will examine upsetting, a process of severe plastic deformation that acts as a mechanical multiplier, compressing the metal to force a stronger internal structure. We will then expose this hardened structure to Dead Sea water, a hypersaline, chloride-rich brine. As the copper concentration increases, the mechanical properties of the alloy improve. The variable we are testing is how this hardened structure reacts to a localized chemical attack. We will reveal how severe mechanical deformation acts as a strength multiplier and why an extreme chloride environment systematically dismantles those mechanical gains. Material science is bound by strict chemical limits. You cannot infinitely add copper to aluminum to scale up its strength. If you add copper beyond this 6% threshold, it stops dissolving into the solution. Instead, the excess precipitates out into separate, brittle phases. This phase diagram charts aluminum and copper. The alloy's behavior is governed by eutectic temperatures, specifically this horizontal line at 548 degrees Celsius. Tracing the intersection along the pure aluminum side reveals the chemical boundary. Copper reaches maximum solid solubility at 5.65%. Because of this limit, tests are constrained to 2% to 4% and a maximum 6% copper. The foundational phase diagram dictates the ultimate structural capacity of the material before any physical deformation begins. These chemical limits manifest directly in the physical reality of the metal's internal geometry. Pure aluminum, in panel A, features a columnar structure with poor strength. Adding 2 and 4% copper forces the grains into a tighter configuration. Reaching the 6% limit triggers a physical transformation into fine grains with scattered copper. Structural strength is driven by the reduction of surface boundary area within these individual grains. When the internal geometry is refined into smaller, tightly packed units, the grain boundaries are less likely to slip or shear under pressure. By pushing the chemical alloy to its 6% limit, we re-architect the metal on a microscopic level to resist physical failure. With the chemistry optimized, we introduce the mechanical multiplier, the upsetting process. By subjecting the grains to severe compressive deformation, we physically store massive energy directly inside the solid metal. This chart maps mechanical characteristics, tracking true stress against true strain. Above the pure aluminum baseline, stress capacity climbs as we increase copper content. Intermetallic compounds hinder the grains from shifting under stress, evidenced by the top 6% curve breaking away. This bar chart measures the impact of the process by tracking microhardness. Notice the blue as-cast samples, dwarfed by the mechanical gains of the deformed samples in red. The data peaks at the maximum chemical limit. The 6% copper alloy achieved a 246% jump in microhardness following the upsetting process. Severe plastic deformation takes the optimized chemistry and locks it into a hard, resistive physical state. Now we introduce the environmental stress test. We take these work-hardened samples and submerge them in Dead Sea water for 21 days. This graph tracks the metric for corrosion resistance, measuring the exact physical mass loss after exposure. The initial results appear positive. Tracing the downward trend, the 6% copper alloy lost the least amount of mass overall. But this reveals a critical materials paradox. Maintaining physical mass does not guarantee that internal structural integrity was preserved. This final chart tracks the actual microhardness readings. Look at the plunge from the work-hardened red bars to the post-corrosion green bars. specifically for the 4 and 6% copper samples. Despite retaining its outward physical mass, the hypersaline environment completely degraded the mechanical strength of the most heavily engineered specimen. This data raises a question. Why does the hardest, most optimized sample suffer the most severe structural softening when exposed to brine? The answer lies at the boundaries of the internal structure. Microgalvanic cells form between the primary pure aluminum, the alpha phase, and the secondary Al2Cu intermetallic phases. High copper concentration creates localized cathodic sites. These boost the anodic activity of neighboring pure aluminum, turning the matrix against itself. Here, halide attack accelerates. Mobile chloride ions target these charged interfaces, unzipping the hardened grain structure from inside out. This paradox illustrates a central logic in modern materials design. The energy trapped within severely deformed, work-hardened grain boundaries becomes a liability the moment it touches a conductive electrolyte. Artificially maximizing a single metric, like pushing physical hardness to its peak, creates a structural vulnerability elsewhere. Successful alloy design involves calculating the balance between phase chemistry boundaries, mechanical processing techniques, and the operational environment. In material science, success is measured by the calculated management of inevitable structural trade-offs.